Hi everybody, good afternoon. This is the last one before lunch I think, so I'll try to keep it short. So I'm going to talk about Coriolis meters, Coriolis flow sensors. I'm not sure, maybe many of you are not familiar with this. So I'll go through a good introduction. So which one? Okay. So to press hard. Okay. There, huh? Okay. So that's the outline of my talk. So I'll briefly give you an introduction of what a Coriolis flow sensor is. We'll talk about some gas entrainment issues, and then give you an overview of the test setup. And we did two kinds of corrections for the errors from the flow sensor. One is based on physics, and one is based on just neural network modeling. And I'll then conclude. So what is a Coriolis flow sensor? So if you have not seen one, it looks like that on the picture there. So the flow of the liquid or gas is coming in the left. It goes through the U-shaped tube and it comes out. So if you cut away the outer metal section, this is what you will see inside. And then what you have inside is the point 3 right in the middle of the U is a exciter which vibrates the U-shaped tubes out of the plane. And there are two pickups that measure the vibration response of the tube. One at 2, which is at the inlet side, and one which is at 4, which is at the outlet side. So very simply, you can get two measurements from this sensor. One is the density of the fluid flowing through the U-tube, and that's related to the resonant frequency. So the higher the frequency, lower the density of fluid. The second measurement you can get is the mass flow of the fluid, and that's related to the phase shift that you will see in the vibration response between the inlet and the outlet. The larger the phase shift, delta T, the higher the flow rate is. So fairly straightforward. So the physics of this sensor is based on the Coriolis force. It's a bit like the gyros. So you have the fluid going through this tube that's being vibrated. You don't have to rotate the fluid completely. So 360 degrees. A vibration is partial rotation. So as this fluid travels through, at the inlet side you will have the Coriolis force downward, which is the cross product of the angular velocity and the fluid velocity. At the outlet side, the Coriolis force is acting on the opposite direction. So this will create a phase shift in the inlet side and the outlet side, and that's what you're measuring. So is there a way I can play this video from here? Or okay. Can you click on the video to play it? So it's probably better to see. So if you have the fluid is not moving, you can see the arrows are not moving. The resonant frequency is proportional to density. But as the flow of the fluid starts to happen, what you will see is there is a phase shift. It flows like a snake. So traditionally, a Coriolis flow sensor will have two tubes because it acts like a tuning fork. As soon as the flow starts to go, it moves like a snake, which that snake-like movement is caused by the Coriolis force, and that causes a phase shift. So right now, when there's no movement, the two sinusoidal waves were in phase, but once it starts to flow, there is a phase shift between the inlet and the outlet side. So this is how a Coriolis flow sensor works. So a lot of, just gauging by the sort of presentations I've seen, not many people may be familiar with Coriolis flow sensors. Is really the gold standard when it comes to hydrocarbon measurement. So if petroleum is being exchanged between two parties, Coriolis flow sensors will be used because they are very, very accurate. Their uncertainty levels can be below 0.1%. So even that's sometimes quite high. So if you're considering buying, I don't know, $200 million worth of crude oil from somebody, and you want to be very, very accurate because that accuracy translates into how much money you're going to pay them more. So you need a sensor that can measure something with very high accuracy. So it can handle a wide variety of fluids. Usually, people use it for measuring milk flow rate, beer, for example. Many process industries use it for chemicals, certain molten plastics, things like that. And it provides two measurements, a density and a mass flow rate. It's a fairly big market, it's growing big time. So there are primarily one big American company called Emerson and another Swiss company called Hauser, E&H, that are the major players here, but there are other companies as well. So I work in the oil industry, so where is this used in the oil industry? I've already told you where we use it for downstream applications where we are selling our crude oil. But in the upstream industry where we are close to the well, so you have a reservoir and you're producing it through a drilled well, and you have something called a choke, which is basically a pressure control device on surface, and you're producing oil, water and gas, and this oil, water, gas will flow through a first stage separator where you get rid of the gas from the liquids. Sometimes you will separate the water as well. Here at the end of the separator you get a gas output, an oil output and a produced water. A first stage separator might just give you a gas output and a liquid output where the oil and water are mixed, the gas is being taken out. Now typically if you, right there, okay, so multiple wells like this will feed into a given separator. So each well will produce slightly different hydrocarbons, slightly different amounts of water. So none of these separators are perfect. So you will end up with some amount of gas which is entrained in the oil phase or the liquid phase, depending on what the output of the separator is. So usually you will use a Coriolis meter at the output of the gas and the output of the liquid or the oil in this case. But as I said, none of the separators are perfect. So even in the oil line, that Coriolis meter that's there to meter the liquid will see some gas going through the meter. So what is the effect of gas entrainment in such flow sensors? Obviously these are designed to measure very, very pure fluids, but when you have small amounts of gas entrained, this will cause a big problem with vibration control of the vibration tubes itself, because the increasing amounts of gas means increasing damping on the vibration itself, which means you need to put more power. There's obviously a limit to how much power you can put into vibrating these tubes because of the safe operation of the tubes requires a limited amount of energy. So, and the other problem is the measurements from the meter itself will be highly erroneous because the density and the mass flow are now out of spec. So if you can play that video, I don't know. So it just shows you what's happening there. So if you have the tube on the left is a pure fluid. So the center of mass of the fluid and the center of mass of the tube are coincident, so there is no problem. But when you have gas entrained in the fluid, you will see that the gas is actually stationary, the tube and the liquid is moving on either side. So the center of mass of the fluid is actually moving, but the center of mass of the tube isn't really. So they are not coincident anymore. That's what causes the errors in the meter. So, what we are trying to do here is to understand what sort of errors happen and try and model these errors out of this measurement. So we took a standard sensor that's available in the market. It can measure from liquid flow rates from 0 to 50 meter cube per hour. It's got some advanced oscillation control. It can provide uninterrupted functionality in the presence of gas, but the readings will be wrong, but it does continue to vibrate the tubes, provide you some measurements. We took the sensor to the Cranfield University flow loop in the UK, tested it under various conditions of gas entrainment. So the liquid flow rate was varied from about 5 to 30 meter cube per hour, and the gas volume fraction within this liquid was up to 50%. And we also tried different, the liquid itself had a different mix of oil and water. The water volume fraction, or in the oil industry we will call it the water cut, is a pure oil all the way to pure water. So the liquid density also was varied in the test. So that's a picture of the process engineering lab. At the far top left corner you can see in the first floor level, that's where the sensor was installed in the flow loop to test it. So I'll go through some graphs. These may be a bit tedious, but I'll try to keep it light. So you see an error in the reported density in the y-axis, and then the gas volume fraction on the x-axis. So as you can see, as you increase the gas volume fraction, the error increases. So you're seeing a decrease here, but it's in the negative scale. So the errors are all negative, and as I said, we have tried 4 different water volume fractions. So for all of them, consistently, they seem to follow the same trend. So, and then the mass flow rate, the other point I want to make here is the error in reported density is always negative, which means the sensor is always under-reporting the density of the fluid when you have gas present in the fluid, in the liquid. The mass flow rate error is a much more complex function. You can see the slopes are changing, and I have color-coded the 0% water and the 100% water here. I've not shown the others because it's a fairly complicated picture of how that error changes. So what we need to do here is to understand how to correct these 2 errors in the reported values from the meter. So as I said, what's the physics behind the errors in the Coriolis flow sensor? So the first error is due to what we call as phase decoupling. So as I said, the center of mass of the tube and center of mass of the liquid are different, which means that the gas is really not following the liquid in terms of vibrating along with the tube, which means that it is physically decoupled, and this causes always a negative error, which means you're always underestimating how much fluid is there within the tube. This is called decoupling. The second is called is due to gas compressibility. So if you imagine the tube is moving to the left and the bubbles are close to the inside wall of the tube, they get pushed against the outer wall of the tube as the tube moves to the left, and the gas gets compressed. Basically, this acts like a dampener. So it's like the suspension in your car. So it absorbs the vibration that has been imposed on the tubes, and this always ends up causing a positive error. This is because the compressed gas will exert a larger force on the tube. So there is a lot of theory behind these 2 errors. So Professor Hemp from Oxford has developed a framework based on a lumped element model. So the lumped element essentially is the mass and the stiffness of the tube, the capital K and the capital M in that model. And then the small k and the small m are the mass and stiffness of the fluid itself. But the stiffness of the liquid, okay, I'll finish soon. So essentially you can work out from a lumped element model like this that the density error is going to be, there are 2 terms in it. One is the phase decoupling error, the first one, and then the second one is the compressibility error. The same for the mass flow rate as well. So what we did was we used that model to correct for the measurements, and when you use the physics-based corrections, so here what you see is the actual mass flow rate in the x-axis and the corrected mass flow rate in the y-axis. They should ideally fall on a 45-degree line, and what I've done is I've plotted 2 sets of lines around this perfect match. One is the plus or minus 5% line, and then the other one is the plus or minus 10% line. So you can see that almost most of them fall within the plus or minus 10% line, but as the higher at the higher end of the mass flow rates, you see some of them actually falling out of even the plus or minus 10% line. So we are able to do some good corrections on the mass flow rate. We also did a neural network model with 4 neurons and 20 layers, hidden layers. We took the 3 inputs, the water cut, the reported density and the reported mass flow rate, and the output was the corrected mass flow rate along the gas volume fraction. We tried a couple of different algorithms, and when you use a machine learning model like this, you are able to push down the error rate so low that then they are actually within the plus or minus 5%. These are almost too good to be true, but I think when you try it in the real world, the performance is likely to be poorer. So anyway, the Coriolis flow sensor that we used was able to handle quite a bit of gas. We were able to correct it based on both the physics-based and a neural-based, network-based model. And we really need lots more data to really train the neural network model for real-life situations, but potentially we can combine these 2 methods. So Thank you.